Can everyone see my screen?
Yeah.
Okay. I'm going to change slides. Let me know if you can see that.
Yeah, we can see it.
All right, nice. So today's lab is on extraction. So what is extraction? Well, it's just a separation method that's used to separate a compound or compounds from one phase to another. And this is achieved by taking advantage of the solubility of the compound or compounds in different solvents. So a lot of you may be familiar with one type of extraction that is common in everyday life. This is a solid liquid extraction. And this is what you actually do when you brew coffee. So you have the solid coffee grounds, right? And you pour the solvent over the coffee grounds, which is the hot water, and you're extracting out the compounds that are responsible for the flavor, for the smell of the coffee, and you're leaving behind the solid coffee grounds. So that's an example of extraction in real life. But in the lab, most of the extractions we do are not solid liquid extractions, they're liquid liquid extractions. And in order to perform the liquid-liquid extraction, we need to use a piece of glassware that's called a separatory funnel. Now, to use this glassware, we have to first fill it with a solvent that contains our compound of interest. And then, so it's a solution with your compound of interest in it. And then we add a second solvent, which we'll call solvent 2, into the separatory funnel as well. And it's very important that these two solvents are immiscible with each other, so they don't mix. So think about water and oil, how you could put them together, but they won't mix at all. And once you mix them, you shake the separatory funnel vigorously, and this causes the liquids to mix, not dissolve into each other, but just to mix, increasing the surface area between them. And this allows for your compound to pass from one liquid phase into the other. Now, why do we use extraction, particularly liquid-liquid extraction? Well, for me, I mainly use this as a purification method in the lab. So if we look to the left, this sample chemical equation, A plus B goes to C plus D plus E plus F. So let's pretend the compound we want is compound C. But we have this reaction and it produces a whole bunch of byproducts. And also it's an equilibrium reaction, right? So we're always going to have some reactants. So what we do is once our reaction is finished and we have a reaction mixture filled with the compound we want, but also filled with a bunch of impurities, we pour that into a separatory funnel. We then add a second solvent. So let's pretend the first solvent was the white one here, and the second solvent is the gray. So we add the second solvent, which is immiscible with the first white one. And the key thing is we want our compound of interest, so compound C, to be very soluble in this second solvent, but we don't want any of the impurities to be soluble in the solvent. So we add it, we shake it up, and our compound of interest, compound C, will dissolve from the white solvent into the gray one. And then we could pour off the gray one and isolate it. And when we evaporate the solvent, we will have pure compound C. Now, in reality, most of the time when you do an extraction like this, it's not only going to dissolve your compound of interest, it might dissolve one or two other impurities, but it's still going to purify your compound quite a bit. So instead of 6 impurities, you might end up with only 2 or 3, which is still incredibly helpful considering that extraction is pretty fast. And not to say that you can't only use extraction, because there's definitely been times where I've used extraction and I've purified my compound just with that. So I'm not saying that it doesn't happen, it's just not that likely. So the theory behind extraction. So I kind of stated the theory before. You just want to use a solvent, a second solvent where your compound of interest is soluble in, but your impurities are not. But how does this happen? So let's take a look at this. This molecule on the left in the separatory funnel, this is caffeine. So let's pretend we have a solution of caffeine in water, and there's other impurities in there that we don't want. We just want to get the caffeine out. So we know that caffeine is very soluble in chloroform, more soluble in chloroform than water. So we add as a second solvent, we add chloroform, which is immiscible with water, and caffeine is soluble in it, which is perfect. Now, before I go any further, I need to say, when you do a liquid-liquid extraction in the lab, most likely you're going to be using a solvent that's composed of water, maybe some stuff dissolved in the water, and another solvent which is a purely organic solvent, something like ether, something like dichloromethane, something like chloroform, like something like that. And it has to be immiscible with the water. Now, the water layer, we call that the aqueous layer, and the layer that's composed of the organic solvent, we call that the organic layer. Okay, so we put our caffeine solution in the separatory funnel, we add chloroform, we shake it, and what do we find? So what we see is not all of the caffeine instantly dissolves in the chloroform, leaving none behind in the water layer. It actually establishes an equilibrium between the water layer and the organic layer. So some will remain in the water and some will remain in the chloroform. But the way it's distributed is dependent on the solubility of caffeine in each of those solvents. So we use what's called a partition coefficient to calculate this. It's a distribution coefficient, KD, and this is calculated by finding the solubility of your compound of interest in the organic layer and dividing it by the solubility of your compound of interest in the water layer or the aqueous layer. So we do this example for this solvent system right here. KD is equal to 8.18. So the top number is the solubility of caffeine in chloroform, and the bottom number is the solubility of caffeine in water. Now we could use this constant to calculate exactly how much caffeine is extracted with one washing of chloroform. So if we assume we have 0.5 grams of caffeine and we're doing the extraction with 50 milliliters of each solvent, so 50 milliliters of water and 50 milliliters of chloroform, we can derive this equation. And it looks complicated, but all it's saying is that X amount of grams of caffeine will dissolve in chloroform, and the volume of chloroform we're using is 50 milliliters, divided by the 0.5 grams of caffeine present in water is going to lose X amount of grams of caffeine to the chloroform layer. And the 50 milliliters comes from the volume of water we use. And what we find is if we use this volume of chloroform and water, that with one washing, we actually extract 0.44 grams of caffeine from our water mixture. And that's pretty good. That's, since we only need to extract 0.5 grams, that's almost all of it. But if we want to get a little bit more, we could do a second washing. So we drain off the first portion of chloroform and we add a new fresh portion of chloroform, and then we shake it again. And if we use the same equation, we find that in that second portion, we will extract 0.053 grams of caffeine. And if we combine those two fractions in total, in two washings, we extract a total of 0.493 grams of caffeine, which is most of it, which is pretty good. And in reality, you will find that since your compound of interest establishes an equilibrium between the aqueous layer and the organic layer, multiple washings are going to be needed in order to extract most of your compound. So like I said before, you'll add one portion, you'll shake it, you'll collect the organic layer while leaving the aqueous layer in the separatory funnel. You add another fresh portion of solvent, shake it again, drain it, so on and so forth. And usually you do it like 3 or 4 times. So in today's experiment, what you're going to be doing is separating a mixture of dimethoxybenzene and benzoic acid just by using extraction. Now, first you dissolve benzoic acid and dimethoxybenzene in diethyl ether, and you create the mixture. And then you're going to try to extract it with water, but there's a problem here because benzoic acid and dimethoxybenzene, they're not very soluble in water at all. But I like this lab because they find a clever way to get around this problem. So benzoic acid isn't soluble in water, but if you were to deprotonate it and make it a charged species, then it would be very soluble in water. And that's exactly what they do. And they do this by, instead of just adding water to the separatory funnel, they add water with some sodium hydroxide dissolved in it. So they add a base and they deprotonated the benzoic acid. We get this intermediate species called benzoate, which is just deprotonated benzoic acid. And when we do the extraction, the benzoate is going to go into the water layer, and you're going to leave your dimethoxybenzene behind in the organic layer. And again, the benzoate is going to establish an equilibrium between the two solvent layers, so you're going to have to do multiple washings. But once you do that, you can drain off the water layer, which contains your benzoate, and you can leave the organic layer behind, which has your dimethoxybenzene, and you collect the dimethoxybenzene in another flask, and you already have your dimethoxybenzene separated, but you still have this benzoate, and we want to convert it back to benzoic acid. So what we do is we clean the separatory funnel, we add the solution back into the clean separatory funnel, the solution containing the water with your benzoate in it. Then we add a dilute solution of hydrochloric acid. The hydrochloric acid is going to reprotonate the benzoate back to benzoic acid. And at this point, you'll see that the water will start becoming cloudy. And this is because benzoic acid actually isn't very soluble in water at all. So it's going to start to precipitate out. So you want to extract it with another solvent, and in this case, we're going to use dichloromethane. So we're going to add dichloromethane into the separatory funnel. And you'll notice that the water layer is gray, but on the right separatory funnel depiction, you see that the water layer goes to the top. And that's because dichloromethane is more dense than water. And it's very important that you keep track of these layers, that you know exactly which layer is the organic layer and which layer is the aqueous layer. Because if you don't know which layer is which, then you don't know where your compound is. And that's very important. So one way to do this is where your table of physical constants comes in. If you look up the density of water and compare it to the density of dichloromethane, you'll see that dichloromethane is more dense than water. So it's going to sink to the bottom while your water rises to the top. So you know my bottom layer is my organic dichloromethane layer, while my top layer contains water and it's my aqueous layer. So you fill it with dichloromethane, you shake it, the benzoic acid is going to go into the dichloromethane, and you drain it off into an Erlenmeyer flask or a beaker or some kind of container. Do a few washings to make sure you get all your benzoic acid out. And what you're leaving behind in the water layer is excess acid, hydrochloric acid. And once you collect all the fractions of your dichloromethane layer or your organic layer, you just evaporate off the solvent and you're left with pure benzoic acid. And that's everything. And my references were the lab manual and this YouTube channel, Chem Survival. Again, I will send everyone these supplementary videos if you want to watch them. They're not required, but they do help understand the process. And he does one specifically with acid-base extractions, which is what we do in this lab. So does anyone have any questions? Okay. So guys, you're free to go. I'm gonna email you the videos that you have to watch for this lab. I believe